In Lesson 1, we looked at a circuit for the most common motor control function, starting a motor at full voltage and stopping it again. In this lesson, we're going to examine many of the common circuits used to provide additional motor functions for AC and DC motors. Let's start with AC motors. One very common motor control function is reversing. All three-phase motors are reversed in the same way, by swapping two of the three power leads. This is done by using an additional contactor with three more power contacts. The two contactors may be mounted side by side and mechanically interconnected, or they may be housed in a single unit called a reversing motor starter. Two of the power line connections to the second contactor are reversed, usually L1 to T3 and L3 to T1. Pushing the forward button energizes one contactor, while pushing the reverse button energizes the other. Since energizing both contactors at the same time would short two of the power lines together, the forward and reverse contactors are always mechanically interlocked. They are electrically interlocked as well, just in case the mechanical interlock ever fails. That's done by wiring a normally closed contact on each contactor in series with the other contactor. As long as one contactor is energized, power cannot get to the other one. Reversing the motor requires pushing the stop button first, which opens the forward contactor, closes the reverse interlock, and allows the reverse contactor to be energized when the reverse button is pressed. This circuit allows the reverse contactor to be energized while the motor is still turning forward under its own momentum. Doing this is called plugging. As we'll see shortly, plugging is one way to stop a motor. However, not all motors should be plugged. The electrical and mechanical stresses are so high that a motor may be damaged. So an anti-plugging function can be added to prevent energizing a motor before it has slowed down enough to be reversed without damage. Anti-plugging requires two normally closed contacts. Often the contacts are part of a centrifugally operated speed switch, which monitors the speed of the motor. One of the normally closed contacts is wired in series with the forward contactor, while the other is wired in series with the reverse contactor. When the motor is started in either direction, the contacts in the opposite circuit open. They remain open during normal operation. When the stop button is pressed, the forward contactor drops out and the circuit is de-energized. But if the reverse push button is pressed, the reverse contactor will not be energized until the motor has slowed down enough to allow the contacts in the speed switch to close. Only then will pushing the reverse button energize the reverse contactor. Now let's take a look at stopping a motor. It can be done in several ways. Most motors are simply allowed to coast to a stop, slowed down by the friction of the loads they drive. Others are stopped with mechanical brakes. But when you've really got to stop a motor fast, you can do it electrically. Plugging is one way to do that. As we said before, that means reversing a motor while it's still running forward. The circuit is very similar to a reversing circuit. Plugging requires two contactors with electrical and mechanical interlocks. The difference is there's no reverse push button. Instead, when you push the stop button, the forward contactor drops out, and the reverse contactor instantly energizes the reverse circuit. Of course, if that were all the circuit did, the motor would simply slow down, stop momentarily, then speed up again in reverse. To prevent that, a set of normally open contacts in a speed switch is wired in series with a reverse circuit. Just after the motor starts, centrifugal force closes these contacts. Power cannot reach the reverse contactor because the interlock contact opens when the forward contactor is energized. When the stop button is pushed, the forward contactor is de-energized. This closes the reverse interlock and energizes the reverse contactor. Now the same forces that had been driving the motor forward try to run it in reverse, which slows the motor very quickly. When the speed of the motor has dropped to a few hundred RPM, the contacts open, interrupting power and stopping the motor just before it would have gone into reverse. Speed switches are usually adjusted in the field to set the moment when the contacts open. If they open too late, the motor may drift into reverse. If they open too soon, the motor may coast forward. Another way to stop a motor electrically is dynamic braking. An advantage of dynamic braking is that it can be used with any induction motor. All that's required for this kind of braking control is cutting AC power to the stator and replacing it with DC through a second contactor. When the DC power is applied, the magnetic fields in the stator stabilize. The stator becomes an electromagnet, which pulls the rotor to a stop very quickly. DC power from an AC to DC rectifier circuit is sent to the stator through the second contactor. As we saw in the other circuits, this contactor must be interlocked with the contactor that supplies AC to the motor. Braking time can usually be predicted in advance, so a time delay relay is often used to remove DC power after the motor has stopped. A centrifugal speed switch may also be used. Two contactors can also be used to run a motor at different speeds, at normal or full speed, as well as at a slow speed. The control circuit is the same one used for reversing a motor. The only real difference is the way the motor itself is wired in the power circuit. Pushing the fast button starts the motor and interlocks the slow contactor, so both circuits cannot be energized at the same time. Pushing the stop button de-energizes the fast contactor, returning the interlock to its normally closed state. This permits the motor to run at its slow speed. When two-speed motors must be started only at their slow speed, this circuit is commonly used. It incorporates a control relay, often called a compelling relay, because it compels the motor to start at the slower speed. The key to the circuit is this normally open contact, which is on the relay. The contact is wired in series with the fast contactor, so the fast contactor cannot be energized until the relay is energized. The compelling relay itself is wired through a normally open contact on the slow contactor, so the relay cannot be energized until the slow contactor is energized. Here's how it works. When the slow button is pressed, power flows to the slow contactor, which closes the contact, energizing the control relay. The relay seals itself in, as well as closes its contact in the fast circuit. The fast contactor will not energize because the normally closed interlock on the slow contactor opens when the slow contactor is energized. Now, the only thing preventing the fast contactor from being energized is the interlock on the slow contactor. You may have noticed that the fast push button does nothing more than interrupt power to the slow circuit. That's because all that's required to change to fast speed is to de-energize the slow contactor. When the fast button is pressed, power to the slow contactor is interrupted. This closes the interlock, and the fast contactor is energized. Changing back to slow speed is simply a matter of pressing the slow push button, which de-energizes the fast contactor and re-energizes the slow contactor. The motor can be switched back and forth at will. The entire circuit is de-energized when the stop button is pushed. Probably one of the most common control functions is jogging a motor and its load into position. It is accomplished with a circuit that allows the seal-in circuit for the motor to be defeated. One common way to do this is with a selector switch. When the selector switch is set to run, the normal three-wire seal-in circuit is maintained. However, when the selector switch is set to jog, the seal-in circuit is opened. Now the contactor coil is de-energized each time the start button is released. When the jogging function is needed in more complex circuits, a control relay is often used. For example, in this reversing circuit, the control relay seals in either the forward or reverse contactor while still allowing the motor to be jogged in either direction. For normal running, the forward run button is pushed. This closes a normally open auxiliary contact on the forward contactor, and the control relay is energized. As in the two-speed circuit we looked at, the relay seals in itself as well as the forward contactor. Power is maintained after the push button is released. The same relay uses a normally open contact on the reverse contactor to seal in the circuit when the motor is run in reverse. When the motor is to be jogged, power goes directly to the forward or the reverse contactor. However, the control relay cannot be energized because these dual contact push buttons for forward and reverse interrupt power to the control relay. When either jog button is depressed, the circuit cannot be sealed in. So when the jog button is released, the motor stops. The major difference between DC and AC motor control lies in the power circuits. While some small DC motors can start at full voltage, most develop inrush currents that are too high. They must be started at reduced voltage. To accomplish this, resistors are wired in series with the armature. When the motor starts, all the resistance is in the power circuit to the armature. As the speed of the motor increases, time delay relays remove more and more of the resistance from the armature. Finally, at full speed, the motor is operating at full voltage. The same method works for all DC motors. Reversing a DC motor is similar to reversing an AC motor. The power leads are reversed. Compound motors are generally reversed by swapping their armature leads. This is done using two interlocked contactors, one for forward, the other for reverse. When the forward contactor is closed, power flows from L1 to L2 by moving through the armature in one direction. When the forward contactor is de-energized and the reverse contactor is energized, power moves through the armature in the opposite direction, reversing the motor. For series and shunt motors, the field leads are usually reversed since they carry less current than the armature leads and are easier to open under load. This is often done with a double-pole, double-throw switch rather than two contactors. With the switch in this position, power flows through the field coil from F1 to F2. When the switch is set in its other position, the flow of power through the field coil is reversed. It flows from F2 to F1. The motor runs in reverse. Another similarity between DC and AC motors is dynamic braking. But dynamically braking a DC motor requires just one contactor. Two normally open contact sets connect and disconnect the armature. Another contact set, this one normally closed, connects and disconnects a resistor across the armature leads. When the contactor is energized, power is supplied to the armature in the normal way, but the resistor circuit is switched out. Pushing the stop button interrupts power to the armature and simultaneously switches in the resistor. With the resistor as a load, the spinning armature generates a current which creates strong magnetic fields. These fields lock on to the stationary magnetic fields of the field coil, and the motor stops very quickly. The AC and DC circuits we've covered on this program are the ones you are most likely to encounter in industry. Whatever a motor controller does, it usually works by using simple circuits like these in combination with each other. If you clearly understand how these circuits work, you will be able to understand the operation of more complex motor control systems.